I am Vijay Shankar Dwivedi, TA in this course. With me, our esteemed professor, Dr. Ghosh, who has been teaching this course in previous sessions. He has covered a lot of materials. We expect that you have some questions. Some of you have put them on the forum also. Due to technical limitations, it is not possible to have an interactive session with you. So I have prepared a list of questions which we will be discussing in today's session. Welcome, Professor Ghosh.
Let me welcome all of you, and let me first confess very clearly that it was my friend Vijay Shankar Dwivedi, who is basically an electrical engineer, and then he did MTech here with me, is the lifeline for this course. I have been getting many feedbacks, especially on the recording part and the board work. You understand, this is the first time we are trying, and I have communicated this to the media center who does all this thing. I am sure our next course will try to add whatever suggestions possible to include, will include. Thank you for suggestions. And talking about Mr. Dwivedi, you could by now you know that he is one of the person passionate and very hardworking, and he and me have one thing common. We are a very, very common man, right? We come from a common background, but we believe in hard work. My personal opinion is, do not unnecessarily give too much weightage to IQ, intelligence, right? All of you can be as intelligent as me, I could be as intelligent as you. It's finally the hard work that matters. Rightly so, the suggestion came because Mr. Dwivedi and his one or two friends were interacting through the forum, and there are some questions. So we'll try to discuss few questions, whatever possible, so that it helps you, right? And as we have promised that this is our Mann Ki Baat session, this is the last session for this course, so we will not keep anything remain unfulfilled. We'll try our best to see that your concepts are clear. However, you are most welcome to contact us through our email IDs and through the forum. We'll still be able to communicate to you.
Let us start with this question. A lot of students has been asking, they want to know, when we already have the lift and drag, then why we need CL and CD?
Yeah, if you remember one of my lectures where we were using Buckingham Pi theorem, and that if you go back to that lecture, you will find this question was answered. When I talk about CL and CD, we are actually trying to take the advantage of geometric similarity and dynamic similarity. That is, suppose it's a non-dimensional, right? CL and CD are non-dimensional. They don't depend upon the dimensional parameters. Suppose you have got an aircraft, very huge aircraft, 30-meter span. Now you want to generate its lifting characteristics. So what best you can do is you can create a geometrically similar model, scale down, and ensure that dynamically they are similar. That is, if the Reynolds number or the Mach number you duplicate inside a tunnel, so then you can match the CL, right? Non-dimensional coefficient you can match, because CL is function of angle of attack, Reynolds number and Mach number, right? So that is why it's easier to work in CL or CD. If you want to match the lift, let's say, then you have to test same size, because lift is proportional to the area, right? You have to duplicate the area, same density, same speed. But here, because in non-dimensional coefficient, we know that CL is function of Reynolds number, Mach number for a given angle of attack. So you just bring down the internal model, scale down smaller model, but ensure that the Reynolds number and Mach number are duplicated. And you will get accordingly the same value of CL, CD, which you can use for your designing of bigger aircraft. So that is the primary advantage of using non-dimensional CL, CD instead of lift and drag. I hope it is clear. You can go back to my lecture, which I have given on dimensional analysis.
Thanks, Professor Ghosh. I don't think there could be any better explanation to it. And the next question is, why we need calibrated airspeed?
I think you should answer this. Please explain.
Sure, sir. Let me try. This is the equivalent airspeed at the sea level for the similar lift. The advantage of this is, we know we have different stall speeds at different altitudes. because with the altitude our density decreases, and to maintain the lift is equal to weight we will require different air speeds. But for the calibrated airspeed, irrespective of our altitude, we have common stall speed. At whatever altitude we are, our stall speed will not change, it will be same. Therefore, if we have the calibrated airspeed, the pilot need not worry to calculate his stall speed at every time. And one more magical advantage of this calibrated airspeed is, for a given rate of climb at whatever altitude we are, our calibrated airspeed will be unique. Let us move to the next question. Why we need infinite wing?
See, the concept of infinite wing is very simple, that for a finite wing, after all, when you are generating lift with a finite wing, the pressure is here more, pressure on top is less, so there will be vortices. So a lot of kinetic energy gets into it, which is typically rotational kinetic energy is extracted out of the airplane, and there is a reduction in the speed, or we say drag has increased. Theoretically, if I have an infinite span, first of all, this loss of drag will be zero theoretically, because there are no pressure difference at the tip, because as an infinite. Second thing is, when you talk about infinite span, for our analysis, we actually mean that there are no cross flows. The flow is moving around the chord, normal to the chord. So our analysis becomes simpler, and we can postulate all of our coefficient, etc., with this assumption, because the moment we have a cross flow, whole the analysis will have to be modified. Okay, so that is one of the advantage of when you talk about infinite span. It is also very clear for you that if it is infinite span, the aspect ratio is also infinite, so the induced drag will be zero. So as a designer, many times you try to fly an aircraft or design an aircraft having a larger span. Larger span means higher aspect ratio, lesser induced drag. But please remember, as you are making the wing span larger and larger, or the aspect ratio larger and larger, there is a possibility that you can increase the area of the wing. If you increase the area of the wing, the skin friction drag will be more. So you need to balance it out. Okay, right?
Yes, and this is like an ideal case when there is no side flow of the air, as a result no induced drag, whereas in our finite wing we have the side flow of the air, as a result we have vortices at the tip, which results into the induced drag.
Right. In a nutshell, when we say infinite span, we are actually talking about a situation where the induced drag is zero and the flow is two-dimensional. Flow is going like this. No flow is going like this or coming like this. Right?
Let us continue our discussion with the next question. Next question reads, how lift is generated? Is it due to the striking of fluid to the wing or due to the pressure difference?
I think you should be able to answer this. You tell, what have you understood?
Okay. I think both reasons are valid, because first is the cause and second is the effect.
Yes.
Due to the striking of the fluid, there is pressure difference, and due to the pressure difference, we have lift.
Right. After all, the lift has to come from somewhere. It cannot come out of nothing. So it is basically momentum exchange, right? Whatever momentum the fluid has, part of that gets created into lift, part of that created into drag, right?
And sir, what is the physical meaning of K and E?
See, when I talk about K, it is, if you see the expression also, it is 1 by pi aspect ratio E, right? As we understand that if aspect ratio is infinite, the induced drag will be zero. So K in some way try to model the variation of induced drag with aspect ratio. Also we know that induced drag is minimum for elliptic distribution. So E is there to model for E equal to 1. It is an elliptic distribution where downward will be same all through. So that is the time where it has minimum induced drag, right? So E equal to 1 corresponds to elliptic distribution, and E less than 1 is non-elliptic, which is 0.8, 0.89, mostly for the wings which generally fly the taper ratio between 0.4 to 0.5. Also understand on this, which I have not discussed, your CD equal to CD naught plus KCL square, right? Even the CD naught changes with the angle of attack, or CL, right? Because as going for different angle, the CD naught may also change, and part of that is also absorbed through E, modified E. You can read Anderson, Introduction to Flight by Anderson, and on the chapter of elliptic distribution, he has talked about it in a small manner, but okay, that's good enough. Right?
So what I understand, this is the proportionality constant for the induced drag. As aspect ratio increases, K decreases, and for the infinite aspect ratio, the K becomes 0. As a result, induced drag becomes 0. Now our wing is 2D. The induced drag also depends upon the pattern of the lift distribution, which is taken care by E, which is maximum for the elliptical distribution.
That means the K, if aspect ratio becomes infinite, the K becomes very small. So the wing will behave more like a 2D wing, or more like its aerodynamic characteristics will be more governed by just the characteristic of the aerofoil. So when you apply aspect ratio correction, the correction required will be very, very less.
And next question for you, what is winglet and what is its usefulness?
As you understand that if this is the wing, finite wing, there are vortices here because of high pressure and low pressure. So one way to discourage this generation of vortices, physically make sure that there are no space for the lower pressure particle to go to the higher pressure at the top. So physically put some surface like this, which are basically concept behind the winglet. By putting winglet, actually you are reducing the induced drag, or theoretically speaking, you are actually increasing the aspect ratio of the wing, because we know as aspect ratio increases, the induced drag reduces. Although the geometrically aspect ratio is not increasing, however, by putting a winglet, since these vortices generation will be discouraged, so induced drag will reduce. So it is equivalent saying I have increased the aspect ratio, I have reduced the induced drag. However, once you put a winglet, make sure that the winglet itself will give some CD0, because it will have friction, skin friction drag. So you have to do optimization what you put. Okay.
And next for you, does CD0 vary with Reynolds number?
You know, CD0 has a major component of skin friction drag, isn't it? So, and you know, as Reynolds number increases, the skin friction coefficient reduces. So if it is flow having very high Reynolds number, high speed flows, your skin friction coefficient will reduce, so your CD0 will start reducing. If the Reynolds number reduces, then the skin friction coefficient will go on increasing, right? That is why when a rocket is fired, when it goes very high altitude, let's say 15-20 kilometers, where density of air is very small, the Reynolds number is very small, the skin friction drag increases. In our language, CD0 increases. Okay? Yes, CD0 has indeed strong function of Reynolds number. That is why when you're going for a scaled out testing, we need to duplicate for a low speed airplane, which is mandatory that we duplicate the Reynolds number, okay, to get an idea about the lift coefficient.
I am asked, what is stall angle?
Yeah, you know, there are many ways of looking into stall angle. You understand that as I increase the angle of attack, the lift increases, the CL increases, not the lift, rightward, the CL increases. At some point, beyond that angle, the flow starts separating, and there is no increase in CL. Instead, there is an increase in the drag. So the stall angle is defined at that angle where the flow starts separating. Or stall angle is the rightest definition of the stall angle is that angle where you get the maximum CL or CL max. Another way of interpreting is this: stall angle is the angle at which you can fly with the minimum speed and still maintain lift equal to weight. So the corresponding speed, I will call it stall speed. Is it clear? V equal to 2W by S by rho CL. So if I am at a stall angle alpha, that means CL is CL max, and so V is the V stall. So it is the minimum speed at which the airplane can be maintained lift equal to weight at a given altitude. There are many ways of interpreting this. You want to add anything on this?
Yeah, from your answer, I got the answer of my next question. The question is, how we decide whether the given angle is advisable or not? And what I interpret from your answer, if my given angle is less than the stall angle, then this is advisable, otherwise it is not. One question which some of our viewers has asked, the viscosity which we discussed, is it dynamic viscosity or the kinematic viscosity?
See, this is a question of definition. When you are defining a Reynolds number as rho u L by mu, then mu is the normal viscosity, and you know dynamic viscosity is mu by rho. Am I correct?
Absolutely.
So if you take the rho in denominator, then you can change it to dynamic viscosity. Otherwise, as per definition, Reynolds number, when you are using rho u L by mu, mu is the kinematic viscosity.
One very pragmatic question: what is the importance of the cruise speed and why we need service ceiling?
So cruise speed is generally when you are designing an airplane, and if it is for cruise mission, you want to select a cruise speed so that your range is maximum, or endurance is whatever you want, and also the maximum speed you also have quite comfortable. Sometimes it happens to fly at a maximum endurance, the speed is very low. And if you are flying all the time with that speed, then you will be reaching a target at a very low, very longer time. So you don't like that. So cruise speed is basically the speed, the design speed for a transport airplane, where you want to select and check that your range is maximum, and you are flying at a such that time taken is also not that large, right? And what is second was that?
Next part is service ceiling.
Service ceiling is, see, as I am going higher and higher, you understand that the engine power and the power required, the gap goes on reducing. So there is an altitude at which, theoretically speaking, you will find the rate of climb maximum will be 0, right, when these two graphs will match at one point. But service ceiling, we say there is a particular altitude where the rate of climb maximum could be 100 feet per minute, right? So that is the concept of service ceiling. And cruise speed is for what speed I can comfortably and favorably design to cruise, and service ceiling is at what height, up to what height I have power to climb, okay? Because that also decides what is the combination of power available and power required, or what is the characteristic of the airplane to have excess power. So you know that I can have a rate of climb maximum at different altitude by different amount. So that also gives additional dimension to an airplane.
So the cruise speed is the optimum speed to travel from one point to another point.
Especially if you are in a transport airplane.
Thanks. This was very precise and to the point. Here is one more question for you. Why do we still have the option of the fixed landing gear when we already have the retractable landing gears?
This is practically, see, theoretically speaking, we always should have a retractable landing gear to minimize the drag, improve CL by CD, all will agree. But when you make an airplane, the cost not only goes in making landing gear, but also maintaining them. So total optimization, if you do, one has to see for the operation for smaller airplane where you have a different type of operation, it may not be advisable to put a retracting landing gear, and you can put it, the cost will go up, the maintenance headache will go up. But for bigger airplane, for longer duration airplane, high speed airplane, not a very low speed airplane, there definitely you have no other option but to go for retractable landing gear, because at those high speeds or for longer duration, it will amount to lot of loss of fuel because of drag experienced by the landing gear. Right?
The next is, why flaps are deployed only during the takeoff and landing? Why not during cruise?
These flaps are primarily deployed during the landing and takeoff to increase the CL max, so that you do not require very large land roll distance either to take off or either to land. Right? Suppose you are using these flaps during the cruise. While I am putting the flap down, a lot of drag increases there, right? So unnecessarily a lot of energy will be wasted, and the engine will be using unnecessary power, and fuel will be consumed, and we don't get anything in that. So that is why it is primarily on landing and takeoff, so that we are flying at a speed lower, much lower, very close to Vstall, and we want larger lift, so that takeoff distance and the landing distance are bare minimum. Anything you want to add in this?
Yes, when we cruise, we have enough speed to get sufficient lift even without using the high lift devices, and at that speed if you use flaps it will increase our drag unnecessarily. Let us proceed with the next question. How ground effect acts on the aircraft and how it affects the takeoff and landing?
At this stage, you just primarily understand that because of ground effect, the induced drag reduces, right? We have given you an expression. When the aircraft is close to the ground during takeoff, during landing, once it lands, I would always like to have a very minimal lift. In fact, zero lift. I don't want any lift that time. All will be the braking. So at this point, rather than going into detail, the ground effect for us, it is basically reducing the induced drag because of reflection of vortices from ground to back to the airplane. It also changed the lift curve slope, but let's not discuss about it. If you read, you will find the downwash also gets changed. So some trimming of the tail also need to be required to be changed because to counter for the change in the downwash. But as a performance course, it is good enough to understand during the ground effect, the induced drag component reduces, right? This KCL square, it will become phi into KCL square, and phi is less than 1, right? Okay.
So the vortices are reflected and induced drag is reduced. And the next question is, when we touch down, why our rear wheels touch the ground first?
Oh, that is primarily for reason that when you are landing, you still want to maintain some large angle of attack so that lift is equal to weight, it doesn't fall like a stone. So that makes us compulsory to ensure that the rear wheel touches first and then the nose wheel to have that angle of attack. There were planes where one can land with the nose wheel also. There are older plane, but then their length will be different, right? But the point is you cannot compromise on the fact that when I am landing, I need a little higher 7 to 8 degrees of angle of attack, so that lift is balancing the weight. Okay.
Yes, it's quite obvious. When we touch down, we need larger angle of attack so that our touchdown speed will be minimum and lesser landing distance. Some of our viewers want to know why the jet engines are described by the thrust required and reciprocating engines by power required.
Yeah, it is actually, the question is not very correct. When you talk about jet, how do I benchmark a jet? Jet is benchmarked by thrust, right? That a small mass of fluid thrown at a higher speed, and there is a momentum exchange, right? But when I come for a propeller-driven airplane, please understand larger mass is thrown back with a smaller speed, okay? However, when you want to, the basic principles, if you see from the energy point of view, they are not very, very different, okay? Not very, very different, though they are not same, definitely. However, one thing you can understand, for characterizing an airplane with a jet engine, it is easy to say this plane is producing this much of thrust. Now, if I talk about the propeller-driven engine, if I say it is also producing some thrust, it is indeed producing some thrust. But if you want to benchmark it, how can you benchmark? One shaft is rotating. This energy is being, it gets the energy from the burning of the fuel. And so we say there is a power available at the brake, okay? And then you attach different type of propeller and extract the power from it. And from that angle, we talk about power rating when we talk about the propeller-driven airplane.
And next, I am asked, does the wind affect the range and endurance?
That you tell, you explain?
Yeah, the endurance has nothing to do with the wind at all, because it's all about the consumption of fuel and the duration of flight. But the range will certainly affected by the wind. If the wind is headwind, it will reduce our ground speed and we will get lesser range. And similarly, if our wind is tailwind, it will increase our ground speed and we will get higher range for the similar fuel consumption.
Very good. Next.
What is glide?
See, when you say glide, see, suppose I throw a stone, right? It also goes like this, it falls like this. I don't call it a glide. Glide means the weight of the body has to be balanced by somebody, and in case of glide, it is balanced by a lift. So instead of falling like this, it goes like this. So that is we call gliding. That is the glide angle is very minimal. So instead of falling like a stone or like a projectile, it actually flies like, so that part of the weight is balanced by the lift produced by the wing. So there are no thrust in this, absolutely. There is no thrust in conventional way of talking about gliding or glide flight. Okay?
In addition to that, we trade off our potential energy, which is because of altitude, and we get forward speed to maintain our lift. And next question is for you, why we ignore buoyancy force on the aircraft? What happens if we consider it?
Yeah, that's very good. See, you are right, there will be buoyancy force, but if I am planning to work on an airship or aerostat or a balloon where the weight of the body material used is very small, then there is a point in talking about buoyancy. Okay? Because buoyancy is nothing but it is the weight of the displaced fluid. Okay? But for aircraft on where material is a metallic material, the weight is so large, so we find that buoyancy component is very, very negligible. So we neglect it, right? Okay, that's the only answer.
Thanks, that was very precise. The next is, why tail is also called stabilizer?
Yeah, this why tail is called a stabilizer, you should be able to explain better than me. Please explain.
Sure, sir. We have already seen whenever there is change in angle of attack, due to the tail, the aircraft has a tendency to nullify this change. And from the control and stability point of view, we can say the tail is providing us a negative feedback. And whenever there is negative feedback, that would be contributing to the stability. That's why we can say the tail is stabilizer.
See, this is the problem. You see, this man is an electrical man. He's a control man. So he explains things in his own language. As we understand, I try to understand language of electrical person who is working in a control. I understand if there is a disturbance at the positive angle of attack, it will the aft tail, the stabilizer, will generate a negative moment, what he calls a negative feedback. And it causes an initial tendency to come back to the equilibrium. So we call it is providing static stability. See how wonderful this merging of electrical and aerospace has happened in Mr. Dwivedi, who is now working on solar UAV. Right? He will soon see that in 1 year, one solar UAV IIT Kanpur will be launching, and the main person who is working as an electrical research scientist, principal scientist on the solar part is Mr. Dwivedi, Vijay Shankar Dwivedi. Yeah.
Our many viewers are confused. Sometimes you plot Cm versus alpha and sometimes Cm versus Cl.
Yeah, that is, see, for symmetric aerofoil or any cambered aerofoil, whether I plot Cm versus alpha or Cm versus Cl, actually Cl and alpha are related, right? Cl equal to Cl alpha into alpha plus Cl naught. So it is the scale only gets changed. However, there is a very good question. If it is a symmetric aerofoil, then whether you put Cm versus alpha and Cm versus Cl, at alpha equal to 0, it will be Cm naught, right? Cm is 0, Cm naught will be there. However, if you are plotting Cm versus Cl, then Cm naught is basically Cm at Cl equal to 0. Now think of a cambered aerofoil. Cambered aerofoil Cl is 0 when? At alpha equal to 0, Cl is not 0. It is Cl is 0 at some alpha positive angle, isn't it? Alpha negative angle, right? See, for a cambered aerofoil, this at alpha equal to 0, Cm is not 0. Because at alpha equal to 0, there will be some Cl naught, right? So for cambered and for your symmetric, when I am plotting Cm versus Cl, we have to be careful at Cl equal to 0, what is the Cm naught. This is the mathematics part. But physical part, when I put Cm versus Cl, I know that dCm by dCl is related to the static margin. Okay? So if I write dCm by d alpha, I cannot write equal to minus of static margin. But if I write dCm by dCl, then I can write dCm by dCl equal to minus static margin, roughly speaking. So that helps me in explaining many things. That helps me as a designer, how much static margin should I keep, what should be the slope of that line, what should be the intercept. But it should be very careful that if I am plotting Cm versus alpha, At alpha equal to 0, whatever Cm is there, that I call Cm naught, and I need a positive Cm naught to trim the airplane at a positive angle of attack. But same Cm naught, if I define at Cm at Cl equal to 0, the value will be different, right? The alpha remains the same. So you have to be careful about it.
We are approaching to the limit of the time. So let us wrap up with this final question, which many our viewers want to know. What is the procedure to visit this flight lab?
See, as far as flight lab is concerned, by now you know Mr. Dwivedi's email ID. They know your email ID, right?
Yeah, I will give my contact details in the end of the session.
You have to simply send an email request either to his email ID or to my email ID. Note down my email ID. It is akg@iitk.ac.in. You send me a mail. It will be good or better if you can plan your visit in a group, right? Maybe 5 to 10 in a group, so that I can plan it. That doesn't mean if you want to come alone, I will not entertain you. You are most welcome. This flight lab has been created by taxpayers' money, and you part of the citizen. You have equal rights as my students have. So most welcome to flight lab, and I'm looking forward to see you sometime in flight lab and exchange one-to-one in person. I hope you have enjoyed. It was our initial experimental effort. We are aware of that. There is a need to improve the recording, there is a need to use a virtual board, and those things are simple things. Most important thing was whether our young community needs such lecture medium or not. And once we get a positive feedback, other things, upgrading it and higher scaling technically is a trivial thing. Most important thing is whether our young people have that enough passion to learn aerospace. If you have that, we are always with you. Thank you very much.
Thank you, Professor Ghosh, for your valuable time. It was really a very informative session for our viewers as well as for me. So friends, this was our final session of this series. We tried to cover as many topics and questions as we could, but we all know questions never end. If you have any query, please feel free to direct them to us. We will try our best to address them. You can reach to us by our web forum, which is hosted at NPTEL website, or you can drop a mail to Professor Ghosh or me. My email address is vijayD@iitk.ac.in. I hope you enjoyed from the session and benefited from this. Apart from technical queries, please let us know about your views on this session. Your feedback is valuable for us. It helps us to improve. That's all I have for now. Thanks for bearing with us. Keep watching, keep learning. Thank you.